This device I'm holding in my hand is at rest, so it wants to stay at rest. Now, if I try to move it this way or move it this way, I'm just trying to accelerate it in a straight line. And the inertia I'm overcoming in that case is the total mass. So if I slide these closer together, then I haven't changed its resistance to accelerating along a straight line. I've changed the position of the mass, but I haven't changed the amount of mass. Now, when it comes to rotating, it's a totally different story. It's at rest, and now I'm going to try to get it out of a state of rest and get it to rotate this way. And not only that, I'm going to try to stop it and bring it back the other way again. So I'm constantly trying to change its rotational rate, and it offers some resistance to that, which I would refer to as some amount of rotational inertia. And that becomes significantly altered by changing the location of the weight. So I haven't changed the amount of mass, but I've changed where the mass is located, and that has a profound effect. It feels like a lot more resistance to my attempts to change its rotational rate. It's what we call rotational inertia has gone up. The symbol for rotational inertia is capital I. Some people choose to use the phrase moment of inertia. These are synonymous, that's interchangeable language. For the two individual masses that are located on this rod, they contribute to the rotational inertia of the system according to this formula. If I take the mass of that object and multiply it times its distance, r, from the axis of rotation, there's r. If I take the value of r and square it and multiply by the mass, that's the rotational inertia from this mass, and I can use this value of r and square it, multiply it by this mass, and I can add the two together and get the total rotational inertia of the two masses. But then again, the empty rod itself has some rotational inertia. If I rotate it about its middle, the rotational inertia is equal to 1/12 times the mass of the rod times its total length squared. If I try to rotate it about its end point, then that changes it to 1/3 times the mass of the rod times the total length squared. So there are formulas for the rotational inertia of different shaped rigid bodies. A rod rotated about its center has a rotational inertia of 1/12 ml squared, a rod about its end 1/3 ml squared. For example, I've included another rigid body calculation that says I can find rotational inertia of a solid sphere as 2/5 mr squared. I believe if it was a hollowed out sphere, like a basketball or soccer ball, it would be 2/3 mr squared. And there's other equations like the rotational inertia for a hoop versus a solid cylinder and so on. So here's an experiment we can do to determine if this formula that says the rotational inertia of a point mass is correct. It goes something like this. We have a compound system. This isn't just a rod rotated about its center, it's a rod with a disc and another rod. So there's just a compound body whose rotational inertia I don't know, but I have the opportunity to make that rotational inertia a bit less by removing a point mass, or I can increase the compound rotational inertia by adding this point mass. And if I added a point mass at the very center, it wouldn't have as great of an effect in increasing this system's rotational inertia as it does when I place this near the end. In fact, I'm going to place it at the 20 centimeter mark on here and lock it in place. Now when I let this go, the object's going to start to spin due to the torque presented by the tension in the string. And when a torque is applied to a system with a rotational inertia, you get a rotational acceleration, an angular acceleration. So let me put the stopper back in place and give you a measurement real quickly. I'm going to measure how far off of the ground this hanging weight is located. So it looks like it's about 79.5 centimeters off the ground. Grab your stopwatches. When I say ready, set, go, and let go of this, you're going to measure how much time it takes for this descending weight to reach the ground. Ready, set, go. rather small angular acceleration, so it takes a significant amount of time. Here it comes, and stop. Okay. Now I'm going to wind it back up, and this time I'm going to count the number of rotations as it winds back up. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how far I had it wound up previously. So as it descends, the system goes through exactly 10 full rotations. This time I'm going to take the additional point mass off. That should reduce the rotational inertia of the system by an amount equal to this amount of mass. We'll call this capital M. So if I multiply capital M times r squared, keep in mind the value of r we're talking about was 20 centimeters. I selected that value. If we subtract mr squared from the system, then we have the new rotational inertia. So this should be less rotational inertia with the same amount of torque, and therefore a greater amount of angular acceleration this time, and it'll fall faster, and therefore reach the ground in less amount of time. Get your stopwatches. 10 rotations, falling the same, 78.5 centimeters. Ready, set, go. Stop. Okay, there's just 2 more measurements I need to give you. Number 1, how much mass was descending. So we have the platform itself is 50 grams, and there's 100 grams on it. So our descending mass is 150 grams. We'll call this one lowercase m. And then I just need to measure what the value of capital M is equal to. So I will provide that value for you afterwards so you can check to see if your answer is right. But for now, I'm going to leave it a mystery and see if you can determine the value of M the long way, based on recognizing the difference in the rotational inertia of the compound system with and without the point mass. Okay, so here's the gist of it and the final calculations you have to make if you want to take it a step further and go beyond making this just a demonstration and into an actual experiment. So you should be able to calculate what the rotational inertia of the system is, as long as we know that the descending mass was 150 grams. If you've measured the time it took to descend once with the additional point mass and once without, and then you also know that the height it fell through was 79.5 centimeters, that's enough for you to determine what the rotational inertia of the system is with the point mass, and then use the other time and figure out what's the rotational inertia without the point mass. In the end, we're going to try to prove that the rotational inertia of just this object by itself adds an additional value of capital mr squared to the system. So you need another formula. In another video, you'll find a setup for how you can derive this equation that says the rotational inertia, whether it's with or without the additional point mass, the rotational inertia of this compound system can be calculated by taking the 150 gram descending mass, divide it by 8 pi squared times n squared. Here n is the number of rotations, which I counted out as 10 rotations. And then that term multiplied by the quantity GHT squared minus 2h squared. The h in this case is the 79.5 centimeters. So you have a small value of time and a large value of time because we did the experiment twice, once with and once without the point mass. So you need to calculate the 2 values of rotational inertia. If you subtract to find the difference between the 2 calculated values based on the 2 different amounts of time, the difference between the value of I with the point mass and without the point mass, the difference is made up by a quantity of capital mr squared. R was 20 centimeters. That's how far away we put this block from the axis of rotation when it was located as part of the compound system. So I'm going to give away the final result. Okay, it looks like the mass of this block is 276.9 grams, just shy of 277 grams. So here's what I'd like you to do. Very simple calculation. Take 0.277 kilogram and multiply it by 0.2 meters squared, right? 277 grams and 20 centimeters. Convert to kilograms and meters. And you can calculate what the value of I theoretically should be for this point mass, and then go about it the long way. Calculate one value of I based on the time it took to descend with the additional mass, and then calculate the value of I again with this formula using the time you got when there was no additional mass on it. Subtract the two values you get for I, and it should be the same thing you get when you use this formula. If so, we have verified this equation.